In this video, we look at some of the mathematical properties of the equilibrium constant, and we're going to relate the equilibrium constant to the reaction quotient. So I'm going to go back and look at this dimerization reaction where 2 moles of NO2 are in equilibrium with 1 mole of N2O4. The concentration equilibrium constant for this reaction is products over reactants yet again. So we've got the concentration of N2O4 divided by the concentration of NO2 squared because we have 2 NO2s. Now, if I was to write the reverse reaction for this reaction here, we would have 1 mole of N2O4 in equilibrium with 2 moles of NO2. It would be a decomposition reaction. So again, I can write the equilibrium constant, concentration equilibrium constant. So Kc would be, in this case, again, it's products, so NO2 to the power of 2 over reactants, so over N2O4. And what you realize fairly quickly is that the equilibrium constant for the forward process and the equilibrium constant for the reverse process are related in this way. The equilibrium constant for the reverse process is simply just 1 over the equilibrium constant for the forward process. So they are the inverse of each other. So let's have a look at a problem. Now we've recognized that the equilibrium constant for the reverse process is simply the inverse of the equilibrium constant for the forward process. So here we go. Carbon monoxide plus chlorine is in equilibrium with CoCO2, and the concentration equilibrium constant for the forward process is 3.9 by 10 to the minus 2, and this is at a fairly high temperature of 1000 K. So it's going to be like, mostly reactants, because this is a pretty small number. There's going to be some products present, but it's going to be definitely favoring the left-hand side. So what about the reverse reaction? Well, here it is written out, the reverse reaction, and I know that K for the reverse reaction is just simply 1 on K for the forward reaction. So it's just going to be 1 on 3.9 by 10 to the minus 2, and this time I get a much bigger number. And so when I think about this, what is it telling me? It's telling me that I'm going to get, a good chunk of that stuff and just have a little bit of that stuff. Right, so they're sort of like consistent with one another, yeah? So this was sort of like a small number, but it wasn't that small, and this is the big number, but it's not that big. So, they're telling you the same kind of thing. So let's go back and look at this reaction here. We've got 2 moles of NO2 in equilibrium with 1 mole of N2O4. And we could write the concentration equilibrium constant for that. And it's going to be products over reactants. We've only got 1 mole of the product, but we do have 2 moles of the reactant. So we have to square the concentration of the reactant. Now, if we multiply everything in this reaction by 4, so the 2 becomes a 4, it becomes an 8, and the 1 becomes a 4, we would have this balanced equation. And I could go ahead and now write the new equilibrium constant for this in terms of the concentrations. And what would I have? Well, it's products over reactants, but this time I'm raising the concentration of my products to the power of 4, and I'm raising the concentration of the reactants to the power of 8. And if you're observant, this new equilibrium constant is simply the one that I had before, but everything has been raised to the power of 4. Okay, so when I multiply my reaction by 4, I raise my equilibrium constant to the power of 4, and that's a general rule. If I multiply everything in all my concentrations in my reactant by some number n, I'm going to raise the value of my equilibrium constant to the power of n. So in general terms, if we have a generic reaction, A moles of A reacts with B moles of B to give C moles of C and D moles of D, we could write the concentration equilibrium constant, where it's just products over reactants, and then if I multiply everything in that reaction by some factor n, and then the value of my equilibrium constant will just be raised to the power of n. So there's a third rule that we're going to look at now, which is what happens when I combine multiple equilibrium reactions to get a new reaction. So we're going to consider this multi-step reaction where we have in step 1 A moles of A reacting with B moles of B to give C moles of C and D moles of D. And again, we can write the concentration equilibrium constant here. It's just going to be products over reactants, where everything is raised to the power of the stoichiometric coefficient. In this second step, we've got C moles of C reacting with D moles of D, which is in equilibrium with E moles of E and F moles of F. And again, the concentration equilibrium constant is the concentration of my products over the concentration of my reactants. And then everything is raised to the power of its stoichiometric coefficient. So what about if I add these two reactions together? Well, that would cancel, and that would cancel, that would cancel, and that would cancel, and I'd get this overall reaction here. Like so. Okay? And so I've got this overall reaction. Can I write a expression for the concentration equilibrium constant? And of course I can, right? Again, it's just going to be products over reactants, and then everything is raised to the power of its stoichiometric coefficient. So what I want to ask now is, can we see a way in which these things are related? How are the first two equilibrium constants related to the one for the overall reaction? So what we can recognize fairly quickly is that if you have a series of equilibrium reactions that you're going to add together, the overall concentration equilibrium constant is given by the product of the concentration equilibrium constants for the individual steps. So for us, in our first step, we had this expression for the equilibrium constant. And for the second step, we had this one. And you'll note if we multiply those two together, the terms will cancel out to give the equilibrium constant for the overall process. So we can use this to our advantage, right? If we have some equilibrium constants, we can multiply them together to get new equilibrium constants. So this is a good example of this. So it says at 1000 K, the concentration equilibrium constant for the following reaction is 1.5 by 10 to the 6. So this is telling us that it's almost all products, right? And then it says at 1000 K, the Kc of the following reaction is 1.4 by 10 to the minus 10. So that's telling you that it's all reactants, basically. Okay? Now, if you look at these two guys here, what you see is that they do have that in common. They have the 2NO2 in common. Now the question asks, calculate the Kc value of this reaction, N2 plus 2O2 in equilibrium with N2O4. Now my expectation is that this is going to be a fairly small number because N2 is pretty unreactive. So let's see what's going to happen. So what I recognize is I'm going to combine 1 and 2 to get this one. So I'm going to take 2 unaltered. So there it is there, I'm just writing that out. And then what I'm going to do is, because I want N2O4 to be a product in my overall reaction, I'm going to flip reaction 1. So this is going to be 2NO2 in equilibrium with N2O4. So this equilibrium constant here gets written unchanged because we didn't do anything to it. We've written the reaction in exactly the same form. However, for this reaction up here, we flipped it. And so what that means that the equilibrium constant for this reverse reaction is just going to be the inverse of the equilibrium constant for this guy. So the equilibrium constant for this reaction is going to be 1 on 1.5 by 10 to the 6. So it's a pretty small number. This is not a very favorable reaction. Okay, so now I add those two reactions together. and I cancel where I can, and I get the desired overall reaction. What will the equilibrium constant be for this overall process? It's going to be equal to the product of the equilibrium constants for the two steps. So I multiply those two numbers together, and sure enough, consistent with my expectations, I got a really small number. Okay, so this is overwhelmingly favoring the reactants, which is what we know. The atmosphere is, 78% nitrogen, 21% oxygen, and it doesn't react very much. That's a pretty stable set of proportions. Okay, so we've just kind of gone through the algebra of how equilibrium constants work, and there are a couple of big ideas in there. What happens when we reverse the direction of a reaction? What happens when we multiply the components of a reaction by some factor? And then finally, what happens when we combine a series of equilibrium reactions to get some new reactions? What we're going to talk about now is reactions that are not actually yet at equilibrium, because we have to keep in mind that the reaction does not instantaneously arrive at equilibrium. It takes a little time to get there. So for a reaction that's not yet at equilibrium, we can calculate this thing called the reaction quotient, and we give that the symbol Q. And the reaction quotient, and I'm just going to illustrate this, is calculated in a very similar manner to the equilibrium constant. So here's this reaction, water vapor reacting with carbon monoxide to give H2O and CO2. And if this reaction is not yet at equilibrium, we can calculate this thing called QC. So that's the concentration reaction quotient. And it has the same form as the equilibrium constant. It's going to be products over reactants, where each of those concentrations is raised to the power of its stoichiometric coefficient, which in this case they're all 1. So, depending on the exact proportions of things when we first mix our reactants together, it's going to kind of determine the value of Q. So in this first case here, case A, we're starting where we have no products and all reactants. And what's going to happen over time is that the reactants get turned into products, and then products get generated, and then eventually we get to a point where we reach equilibrium, and then the amounts of our reactants and products stays the same. So when we're out here, when we have too many reactants and not enough products in order to be at equilibrium, what's going on? So what's happening is that we don't have enough products, so Q is going to be too small. Q is going to be less than K. And so when we have not enough products and too many reactants for the system to be at equilibrium, Q will be less than K, and the system will spontaneously move towards products in order to bring Q equal to K. If we start the other way, where we have exclusively products and we have no reactants, well, what's going to happen is the reverse reaction will occur, and we'll be turning our products into reactants. So our product concentration will decrease and our reactant concentration will increase until we get to equilibrium, and then everything will be stable from there on out. Now, if we have too many products, when we look at our expression for Q, our top line will be too big and our bottom line will be too small. The net result of that will be that Q will be greater than K. If we have too many products and not enough reactants, Q will be greater than K. And when Q is greater than K, what's going to happen is we're going to turn spontaneously products into reactants. If we measure Q and see that it is equal in size to K, then no change is going to happen. The amount of products and reactants will remain constant. So one thing that we'll often do is we'll measure the value of Q. So we'll measure the concentration of everything and calculate Q, and then compare that to the known K. And if Q is less than K, we know that the reaction will spontaneously go towards products. And if Q is bigger than K, we know that the reaction will spontaneously go towards reactants. So Q is a very useful quantity that tells us the direction that the reaction will move. So this is kind of illustrated here. If we determine Q and find that it is less than the known K, then the reaction will spontaneously move towards products. If we determine Q and find that it is greater than K, then the reaction will spontaneously move towards reactants. If we measure Q and find that it is equal to K, then nothing is going to happen. So here's an example problem. It says the value of the concentration equilibrium constant for the following reaction is 4.7 at 373 K. So 373 K is like, around 100 degrees Celsius. So 4.7, it's not really that small, but it's not that big. I'm going to say it's going to be like mostly reactants with a little bit of products. It says, is a mixture of the two gases in which the concentration of NO2 is 0.025 and the concentration of N2O4 is 0.0014 moles per liter at equilibrium. If it's not at equilibrium, in which direction will the reaction proceed? So what I've got to do is calculate Q and compare it to K. So my expression for Q, remember, it's going to be products over reactants. So it's going to be N2O4 raised to the power of 1, because there's only one of those guys, divided by NO2, and that has to be squared because there's two of them. So that's what I've got here. So Q is going to be equal to 0.0014 divided by 0.025 all squared, and that gives me a value of 2.24, which is not 4.7. So I know that the reaction is not at equilibrium, so it's going to shift to either the left or the right and to come into equilibrium. As Q is less than K, that means that I don't have enough products, right? I need to make Q bigger in order for it to be equal to K. So what's going to happen is the reaction will spontaneously move in the direction of the products, or a chemist might say the reaction will move to the right. Okay. So we only have one last little thing to mention regarding equilibrium constants and reaction quotients. And that's concerned with when we have heterogeneous systems, that is, we have multiple different phases, things get a little weird. So most chemical equilibria are in fact heterogeneous, and that is that there is more than one phase present. So this is a classic precipitation reaction. An aqueous solution of sodium chloride reacts with an aqueous solution of silver nitrate, and this forms an aqueous solution of sodium nitrate and silver chloride, which is a solid. Now, something that's worth noting is that, or worth thinking about, is what is the concentration of solid silver chloride? And what you realize when you think about the concentration of a solid, remembering that concentration is just moles per unit volume, you realize very quickly that this, for a solid, is always a constant. It's a constant for a solid. So the concentrations of pure solids are constant at a given temperature. They don't vary. And so we as chemists have decided that we are not going to include the concentrations of pure solids in our expressions for Q and K. Now, there's a similar thing that happens with liquids, right? So here again is a heterogeneous equilibrium. We've got aqueous, we've got a liquid phase, we've got an aqueous phase and an aqueous phase. And what you see is that the concentration of pure liquids doesn't ever change either, right? Because remember, the concentration is just the moles in a given volume. And for a pure liquid at a constant temperature, that is a constant for liquids. Okay, so the concentrations of pure liquids are a constant at a given temperature. So again, what chemists have decided is that they will not include the concentration of pure liquids in expressions for K and Q because they are constants. So we are only interested in concentrations that change as we move towards equilibrium. Terms for pure liquids and pure solids are not included in expressions for Q and K. So if I'm going to write the expression for the concentration equilibrium constant for our precipitation reaction that we were looking at previously, I'm going to omit the concentration term for the silver chloride solid that is produced. And so Kc will just be the concentration of NaNO3 divided by the product of the concentrations of NaCl and silver nitrate. So this guy, which is a constant, kind of just gets incorporated into our value for Kc.